Hello and welcome to tutorial number 11. Our topic today is intermolecular forces of attraction and heating curves. Before we get started, just a quick reminder that the notes to accompany this tutorial are available online through my website. With that said, let's go ahead and get started. So we're going to start out with just a little bit of review today. We already know that ionic compounds form when an atom transfers its valence electrons to another atom. And the result is positively charged cations and negatively charged anions. And those oppositely charged ions attract one another very strongly via electrostatic forces of attraction. And those attractive forces are so strong, they are so significant that ionic compounds will be solids at room temperature, atmospheric pressure, and they will have very high melting points and even higher boiling points. So let's write a little bit of that review down on the board. Okay, ionic compounds. In ionic compounds, the oppositely charged ions attract strongly via electrostatic forces, and those electrostatic forces of attraction are so strong that ionic compounds will be solids at room temperature, atmospheric pressure, and they will have very high melting points. I'll just write MP for melting points, and very high boiling points, BP for boiling points. Okay. Well, what about molecular compounds? Well, we know that molecular compounds form when atoms share their valence electrons to form covalent bonds. And molecular compounds, therefore, are not charged. They are not composed of cations and anions. They are composed of uncharged units called molecules. Well, the attractive forces that exist between molecules in a molecular compound can vary widely, because we know there are lots of examples of molecular compounds that are solid at room temperature, atmospheric pressure, but there are many that are liquid and many that are gases. So a wide difference in the attractive forces that exist between molecules of molecular compounds. So let's just write a little bit of that down here. Okay, so molecular compounds. So we know that they can be solids at room temperature, atmospheric pressure. Let's just write down one example. How about sucrose, table sugar, something that everybody's familiar with. Sucrose is composed of carbon, hydrogen, and oxygen. It has the formula C12H22O11. And of course, that's a solid at room temperature, atmospheric pressure. Let's think of a liquid. Probably the most common example would be water. Water is a molecular compound, formula H2O. And let's think of an example of a molecular compound that is a gas at room temperature, atmospheric pressure. How about carbon dioxide? We could think of many, I'm sure, but we don't want to get carried away. So carbon dioxide, that's a good one. CO2. Let's put those in parentheses. Okay. So the solids and liquids must have pretty significant attractive forces between the molecules. So I'm going to write that here. Solids and liquids have significant attractive forces between the molecules. whereas gases would have negligible or no attractive forces between the molecules. Remember that in the gaseous phase, the particles of the gas, in this case we're talking about a molecular compound, so I'll say the molecules have obtained so much kinetic energy that that kinetic energy has overcome all the attractive forces between the molecules. So I'm going to write that here. No attractive forces the kinetic energy, you can think of that as the motion, kinetic energy of the molecules has overcome any attractive forces between the molecules. Okay, so our tutorial today will be focusing on these attractive forces that exist between molecules in a molecular compound. And there are 3 different types of intermolecular forces of attraction. Intermolecular meaning between the molecules. Intermolecular means between the molecules. So these intermolecular forces of attraction, and they're already described for you on slide 2. So let's go ahead and erase here and go on to intermolecular forces of attraction. Okay, 3 types of intermolecular forces of attraction. So I'm going to write types of, I'm going to write IFAs just to save a little time. I'm always going to write IFAs to abbreviate intermolecular forces of attraction because it's kind of a long thing to write. All right, so we're going to start with dipole-dipole, or what's sometimes called dipolar forces of attraction. I know that in the notes I wrote London dispersion forces first, but I think that dipole-dipole is an easier force of attraction to understand. So I'm going to go ahead and start there. So let's start with dipolar forces, also known as dipole-dipole. And dipolar forces exist between polar molecules. And they form when the partial positive end of one polar molecule attracts the partial negative end of another polar molecule. Okay, so I'm going to write that here. The partial positive end of one polar molecule attracts the partial negative end of another polar molecule. Okay, so let's go ahead and draw this for HCl, which was one of the examples we used in tutorial number 10 to show or teach what a polar bond is. And you might remember we checked the delta En and we calculated that this bond would have uneven electron sharing and that the chlorine would be winning the tug of war for the electron density and therefore have a partial negative charge, leaving our hydrogen partial positive in charge. Okay. So then the partial negative end of an HCl molecule we would expect to be attracted to the partial positive end of another molecule. So I'm going to go ahead and draw another one here. Okay, and I'll indicate my partial positive and partial negative charge buildup. Okay. Now, since there's lots of different polar molecules, this was just one example, I'm going to go ahead and indicate this in a more generic way as well. So remember in tutorial 10, we also indicated the uneven electron sharing with this sort of cartoon diagram where these were the nuclei, the nucleus for the hydrogen and the nucleus for the chlorine, and then we showed that the hydrogen side had less electron density. This cloud is showing the electron density. The chlorine had more. Okay, so this was our partial negative charge buildup on this side, leaving this side partial positive. Okay. So anytime you have a polar molecule, that partial negative end will attract the partial positive end of another polar molecule. So let's make this partial positive, partial negative. All right. So again, I think that one is the easiest one to understand, and that's why I like to start with that one. Now, that being said, this is for polar molecules only. This describes the attractive forces that would exist between polar molecules, which have partial positive and partial negative charge buildup. Nonpolar molecules do not have partial positive and partial negative charge buildup. So how do nonpolar molecules attract? We know that some nonpolar molecules have pretty significant intermolecular forces of attractions because there are nonpolar molecules that are solids at room temperature, atmospheric pressure, indicating very strong intermolecular forces of attractions between the molecules. Iodine is a great example of that. It's nonpolar, but it's a solid at room temperature. I'll just write T for temperature, and atmospheric pressure. I'll just write P for pressure. So why? What are those intermolecular forces of attraction that are attracting those iodine molecules together so strongly? Let's talk about that next. I'm going to erase here first. Okay, London dispersion forces. London dispersion forces of attraction result from the constant motion of electron density that can result in an instantaneous dipole. I'm going to write that here. Result from constant motion of electrons which forms instantaneous dipoles. Okay, so for this, for an example of this, let's go ahead and stick with iodine, because that was the example that we just gave a moment ago. Okay, so I'm going to draw the Lewis structure here. We know that it is a nonpolar molecule because the delta EM between the two iodine atoms has to be 0, right? So no partial positive, no partial negative charge buildup within this molecule. It is a great example of a nonpolar molecule. So if we redraw this in that sort of cartoon diagram that I used before, where I show the nucleus for each iodine atom and then just the even electron density that's being shared in this bond. It's represented by this cloud here. Well, this cloud of electron density, the electrons are in motion. They're moving about. And so at any given time, the average, I would say, the electron density is evenly shared, as we have it indicated here. But at any moment, at an instant, there could be a time where that electron density is pushed to one side or the other. Okay, so that would result in what we call an instantaneous dipole, a momentary unevenness in the electron density. So therefore, a moment where there is a partial negative and a partial positive charge buildup, even within this nonpolar molecule. Okay, so I'm going to write here, this is called an instantaneous dipole. It's just an instant where the electron density has been pushed to one side or the other side of the molecule, creating a temporary, momentary, partial positive and partial negative charge buildup. Now, the fact that it exists, even for that one little instant, means that it can then affect other molecules that surround it. So you can imagine another molecule right next to this one where the electron density was being shared evenly, but now this partial positive charge is going to start drawing some electron density toward itself, and that induces yet another instantaneous dipole. So I'm going to draw over here. And now there are two of them. We've got our partial negative charge, partial positive charge. And there would be attractive force between these. I'll just do a little dashed line for my attractive force. Okay, so this only happens for an instant, right? This dipole is only created for an instant, and then it goes away. It goes back to that equal electron sharing, the nonpolar molecule. But the fact that it exists even for just an instant means that it can affect all the molecules around it, start affecting the molecules around it, and then once it's gone, those molecules, which now have instantaneous dipoles, can affect the molecules around them. So you can imagine that at any given moment in this sample, there would be some instantaneous dipoles, inducing new instantaneous dipoles. And so even though they disappear, other dipoles have been induced for a moment, and then they disappear. There are new instantaneous dipoles, and so this is constantly happening within the sample. And it can be a very significant force of attraction. It's very much dependent on the size of the molecule. Okay, so let's write that here. Dependent upon the size of the molecules. That is, the larger the molecule, the more electron density there is to be pushed around, and the greater this instantaneous dipole can be. Okay, so larger molecules tend to have greater London dispersion forces of attraction. I'm going to write that down here because I don't have room up here. So larger molecules have more electron density to move around. And therefore have greater instantaneous dipoles and greater London dispersion forces of attraction. I'm just going to write LDF for London dispersion forces of attraction. It's kind of a long thing to write out. Okay, so a good example of this would be comparing some of the other halogens to iodine, which we used as our example up here. We said that iodine is a solid at room temperature atmospheric pressure, meaning that it has pretty significant intermolecular forces of attraction, which happen to be the London dispersion forces. But look at the other halogens. So I'm going to write example here. We'll just use chlorine, Cl2, which look very similar to iodine, except it would be much smaller. So go ahead and take a minute to look at your periodic table and prove that to yourself. Look at the position of chlorine, look at the atomic mass of a chlorine atom, much smaller. You can even look at the electron configuration, much fewer electrons than iodine. Okay. And then let's look at bromine. So this is supposed to represent Cl2. I'm going to make bromine bigger. You can look at the periodic table and you can prove to yourself that bromine would be bigger than chlorine. And then iodine would be the largest one of all these three. Okay. And if you looked up the melting points and boiling points for these three substances, you would see that chlorine is a gas. Its melting point and boiling point are both below room temperature. It has boiled long before the temperature of room temperature, which is around 23 degrees Celsius. Bromine is a liquid at room temperature atmospheric pressure, stronger intermolecular forces of attraction, still just London dispersion forces, but they are stronger because of the size of the molecule being much larger than the chlorine molecule. And iodine, being larger still and having greater electron density to push around, greater polarizability, greater instantaneous dipoles, is a solid at room temperature atmospheric pressure. So still just London dispersion forces of attraction, but they are much more significant for the iodine molecules. Okay, so that's what we mean when we say that the size is a factor here. The larger the molecules, the more electron density there is to push around, the greater the polarizability. All right, we're going to go ahead and erase here and go on to hydrogen bonding. Okay, hydrogen bonding. Hydrogen bond is really just a special type of dipolar force of attraction. In a hydrogen bond, you have a hydrogen atom that is covalently bound to a highly electron-negative element, either oxygen, nitrogen, or fluorine. And then that hydrogen atom, which is very partial positively charged, is being strongly attracted to another highly electronegative atom within a different molecule. Again, either O, N, or F. Let's write that down. Okay, so it's a special type of a dipolar force of attraction where a hydrogen atom is covalently bound to a highly electronegative, I'm just going to write En for electronegative atom, either oxygen, nitrogen, or fluorine, and attracted to, attracted to another highly electronegative atom. Again, either O, N, or F. Okay, so let's draw a picture to help us understand this better. Let's use water as our example. It's a great example of a molecular compound that's capable of forming hydrogen bonds. So I'm going to draw the Lewis structure. I'm going to draw it quickly because we already learned how to do that in a previous tutorial. So I'm going to draw a Lewis structure for water. You might remember that water is polar with a partial negative charge buildup on the highly electronegative oxygen, leaving the hydrogens partial positive. Okay. And then I'm going to indicate my hydrogen bond, my intermolecular force of attraction, with the green dashed line. So I'll show this hydrogen participating in a hydrogen bond to another water molecule. Okay. So it would be attracting the highly electronegative oxygen. It's going to be attracting the lone pair electron on that oxygen atom. And of course, in this water molecule, we also have the partial negative and partial positive charge buildup. And so this whole complex, the presence of this hydrogen atom here, which is covalently bound to this oxygen, and also strongly attracting the highly electronegative oxygen of another water molecule, it's this whole complex that contributes to the hydrogen bond. So I'm going to circle this whole thing right here. Okay. Now you might be noticing that this water molecule actually has 4 potential sites for hydrogen bonding. One little water molecule can actually form 4 hydrogen bonds to 4 different water molecules. Let's go ahead and draw that right now. So this hydrogen can form a hydrogen bond, but so can this hydrogen. It is also covalently bound to oxygen, so it can also attract the lone pair of electrons on that highly electronegative oxygen of another water molecule. But notice our oxygen can also participate. Each lone pair of electron can be lent to the formation of another hydrogen bond. Let's go ahead and draw. This time it would be attracting the hydrogen from another water molecule, like so. Okay, so 4 potential sites for hydrogen bonding within just one little water molecule. 2 opportunities on the oxygen atom to attract the partial positive hydrogen of 2 different water molecules, and 2 opportunities for the partial positive hydrogens to be attracting the partial negative oxygens of 2 other water molecules. Okay, so hydrogen bonding is a very significant intermolecular force of attraction. It causes substances to have much higher boiling points than we might first assume. So let's just take a look at a molecule that looks very much like water. Let's look at H2O versus dihydrogen monosulfide. Okay, very similar molecules. If you look at their Lewis structures, they look almost identical. They have the same molecular geometry. But the boiling point of water is 100 degrees Celsius. And that's due to the fact that those hydrogen bonds are a very significant intermolecular force of attraction, and it takes an awful lot of heat energy to start breaking those intermolecular forces of attraction, those hydrogen bonds, apart. Whereas the dihydrogen monosulfide has a boiling point of about negative 60 degrees Celsius. So it is a gas at room temperature, atmospheric pressure. It has boiled at negative 60, it boils at negative 60 degrees Celsius. And that's because of the lack of the opportunity for dihydrogen monosulfide molecules to hydrogen bond with one another. If you look at these bonds and you calculate the change in electron negativity, you'll find that a sulfur hydrogen bond is only a delta En of 0.4. That's not even polar covalent. So there's no partial positive and partial negative charge buildup at all within this molecule. And so these hydrogens cannot participate in hydrogen bonding. Think about that and make sure that it makes sense to you, because A lot of introductory chemistry students will say, well, it's got hydrogen. It should be able to hydrogen bond, right? Not true. It has to have a hydrogen that is covalently bound to a highly electronegative atom, either oxygen, nitrogen, or fluorine. That leaves the hydrogen super partial positively charged and ready to attract some partial negative charge. All right, hopefully that makes sense. Before we go on to our last slide, which is slide 3, and talk about heating curves, I just want to say a few more things. So let's go ahead and erase right here, and I'll write a couple more bullet points on the board. Okay, so some last points that I want to make here before we go on. First thing is that a hydrogen bond is just a type of intermolecular force of attraction. It is not a covalent bond, okay? It is a force of attraction that exists between two separate molecules. It's a very strong intermolecular force of attraction. It's a very significant one, but it is still just an attractive force for two different molecules can have for one another. Okay. The second point that I want to make before going on is that all molecules have electron density that's in motion, and therefore all molecules are capable of pushing that electron density around, which means that all molecules, whether they're polar or nonpolar, are capable of exhibiting London dispersion forces of attraction. Okay, nonpolar molecules are only capable of exhibiting London dispersion forces of attraction for one another. Polar molecules are also capable of dipolar forces of attraction. And if that polar molecule contains a hydrogen that is covalently bound to either O, N, or F, then it is capable of that extreme or special type of dipolar force of attraction known as the hydrogen bond. So I'll just really quickly summarize those points right here. Okay, so we said first that a hydrogen bond, I'll just write an H bond, is not a covalent bond. Okay, it's still a type of intermolecular force of attraction. Okay, and then I said that all molecules are capable of London dispersion forces of attraction. I'll just write LDF because all molecules have that electron density that's in motion that can be pushed around within the molecule. Okay. But nonpolar molecules have London dispersion forces only. They're not capable of any other type of intermolecular forces of attraction. Polar molecules are also capable of exhibiting dipole or dipolar forces of attraction. And then last but not least, last thing I said was that when a polar molecule has a hydrogen covalently bound to O, N, or F, it's capable of the special type of dipolar force of attraction called the hydrogen bond. So let's write here, if a polar molecule has hydrogen covalently bound to either oxygen, nitrogen, or fluorine, it is capable of a special dipolar force known as hydrogen bonding. Let's write H bonding. Okay, so just some last minute notes. All right, let's go ahead and go on to slide 3, heating curves. Okay, we're going to go ahead and look at heating curves next, and we're going to take more of a qualitative approach to this and just get an idea of how a heating curve is shaped, what the shape of a heating curve is, and what the different lines in a heating curve represent. Okay. So a heating curve is going to have the same generic shape regardless of what substance it's representing. So we're going to really focus on that generic shape. Okay. And in a heating curve, we have heat. We'll just write kilocalories per mole for the unit here. It doesn't really matter since we're not really being quantitative here. I'll just go ahead and give it units. Versus temperature. And we'll go ahead and put that in degrees Celsius. Okay. And a heating curve will always have the same general shape. You're always going to have a line followed by a plateau. The plateau can be longer or shorter depending on what substance it is and what the heat of fusion for that substance is. And then that's followed by another line and another plateau. And again, that plateau can be bigger or smaller depending on what the substance is and what the heat of vaporization is. And then finally, one last line. Okay, the first line will always be representing the solid state of the substance. Okay. The second line is the melting point of the substance. The third line is where the substance has melted but not yet boiled, so that's the liquid state. The next line, the plateau, is the boiling point of the substance. And the last line is after the substance has boiled, so the substance is in the gaseous state. Okay, so let's just go ahead and do this heating curve for water, because we happen to know the melting point of water is 0 degrees Celsius. Let's write H2O here for water. And the boiling point is 100 degrees Celsius. So that makes it easy for me to mark off that this melting point reflects 0 degrees Celsius and that this boiling point is reflecting 100 degrees Celsius. Let me just move that so I can fit this all here. There, okay. All right, so that's supposed to line up with the melting point. That's supposed to line up with the plateau for the boiling point. So let's take a look at what's happening to these water molecules starting from here. Okay, so we know this temperature is below the melting point, so we're talking about water in the solid state. In the solid state, we would expect any substance, really, to have the maximum number of intermolecular forces of attraction between molecules. So I'm going to write max number of IFAs. IFA stands for intermolecular forces of attraction. So for a water molecule, we know that that would be 4 hydrogen bonds per water molecule. And that helps us to see why those water molecules would be really locked in a tight, rigid, solid structure in this phase. Okay, so I'm going to go ahead and draw my water molecule. And I'm going to draw the hydrogen bonds with dashed lines here to my 4 other water molecules. I'm going to draw those maximum intermolecular forces of attraction, which would be my 4 hydrogen bonds. I've got one here to the oxygen of another water molecule. Same thing over here. Over here, the oxygen is attracting the hydrogen of another water molecule. And this oxygen has 2 lone pair of electrons, so it can form a hydrogen bond, not just to 1, but to 2 different water molecules. So here's a hydrogen bond, here's a hydrogen bond, here's a hydrogen bond, here's a hydrogen bond. Okay, so 4 hydrogen bonds. Well, as the temperature, or as heat, I should say, as heat is added to this water in this solid state, with all its hydrogen bonds holding it in that tight, rigid structure, what starts to happen to those molecules? Well, we know that as the temperature increases, that the motion, the kinetic energy of the particles of a substance will also start to increase. So you can kind of imagine those water molecules, they're in there, they're moving around a little bit. As the temperature rises, they start to move more and more and more, and they're kind of vibrating more and more and more. And eventually, we reach the melting point of the substance. Notice that as the heat energy continues to be added, the temperature plateaus. What's happening to those water molecules at the melting point here? Well, all that heat energy is going into breaking apart some of these intermolecular forces of attraction, so that now the water molecules don't have that maximum number of IFAs, 4. They have fewer than the maximum number of the IFAs. So I'm going to write here that heat energy is used to break apart some of the IFAs, intermolecular forces of attractions, so that we no longer have the maximum number of intermolecular forces of attraction. We no longer have those water molecules locked in that tight, rigid, solid structure. The substance has reached its melting point. And above that temperature, in the liquid phase, let's go ahead and write fewer than the maximum number of IFAs. Because we know at the melting point, some of those intermolecular forces of attraction were broken apart. And that's why your liquids will have more freedom for the molecules to move around, to slide past one another, to trade places, to flow, in other words, to flow, because they aren't locked into that tight, rigid structure. You can imagine if these 2 intermolecular forces of attractions broke apart, now this water molecule can start spinning around, not just vibrating in one place, but actually spinning around. And if another one breaks, it could actually start to slide past some other water molecules. So there's where the flow of the liquid comes in. Now we're going along as we increase, as the heat energy is added, the temperature increases more and more and more. And so we can imagine what's happening to those water molecules. They're starting to move around and slide past one another faster and faster and faster and faster and faster, gaining more kinetic energy, more motion, until we once again reach the boiling point, the plateau here. And at this boiling point, at this phase change, all of that heat energy that's being added is no longer increasing the kinetic energy here and increasing the temperature of the substance, but instead it's being used to break apart all of the remaining intermolecular forces of attraction that exist between those water molecules. So right here, heat energy used to break apart all IFA, so all of the intermolecular forces of attraction that remain at that boiling point, they're being ripped apart. Very important here, the covalent bonds in the molecule that hold the atoms together are not being ripped apart. That would be a chemical change. And we know that phase changes are just physical. Okay, so it's water, H2O, in the solid state. It's water, H2O, in the liquid state. and it's water, H2O, in the gaseous state. It's the intermolecular forces of attraction between those water molecules that are being ripped apart at the melting point and then further at the boiling point. Okay. And then in the gaseous phase, we would have no intermolecular forces of attraction between those water molecules. And so those water molecules have now obtained enough energy, enough kinetic energy to overcome all the intermolecular forces of attraction, holding them together in the liquid phase. And that's what happens when a substance boils and enters into the gaseous phase. We've ripped apart all the remaining intermolecular forces of attraction. All right, so any heating curve is going to have the same generic shape. I think it's important to understand what these different lines mean. So make sure you understand that that first plateau is always going to be your melting point. Okay. That second plateau is always going to be the boiling point of the substance. And it's going to vary, you know, what it is. It's not always going to be 100, right? Because we're not always going to be talking about water. Okay. And then of course it's very important to know that below the melting point we're talking about the solid state of the substance. Above the melting point, below the boiling point, we're talking about the liquid state of the substance. And above the boiling point, we're talking about the gaseous state of the substance. Okay. All right, this will conclude our tutorial number 11. I hope you will consider tuning into our problem set number 11. Thank you very much.